Thank you very much, John. Thank you. So, welcome everyone to this talk. So, I will be going through some of the possible evolution of backhaul technologies for 5G networks. So, my talk is linked with both the morning slots talks that you heard from Misha Dollar as well as from John as well. So, I will have a brief overview about the 5G challenges that will really affect the backhaul requirements. And that will really touch some of the visions that Misha mentioned, how they translate into actual numbers and how those numbers or those requirements, they describe how backhaul has to be evolving in next few years. And I will also talk about how Cloud RAN or centralized RAN techniques, they affect the backhaul requirements depending on what kind of final objectives we want to achieve in terms of spectral efficiency and other parameters. And then I will show you some initial or recent results that were presented at ICC 2015 as well about an adaptive backhaul aware cell range extension approach and identify some future research directions that are currently very active in this area. So starting with the first 5G challenges, we saw what kind of applications we are working for, and of course that translates into some very high numbers. Some of them they were mentioned by Misha in the morning as well. So we want to have 1 gigabits per second even in very densely populated challenging wireless environments as well. And of course tens of megabits per second should be a norm for the 5G services. This translates to a factor of some people say 100, or some people are more ambitious and say a factor of 1,000 in terms of data traffic volume. And this also requires massive machine-to-machine support as well, as mentioned in the morning as well again. So we need several hundreds of thousands machine-type devices in one cell that need to be supported. Okay, this comes with two other very interesting challenges. So one is we do not want the complexity to go enormously high, because complexity also means energy consumption on the devices. So we want to have a very long battery life, not for the mobile devices, but I will mention what kind of devices we are mentioning when we say greater than 10 years. So machine type of devices or sensor devices. And we also want to have tactile internet, which was mentioned in the morning. Now, tactile internet has a very, very stringent latency requirements. As said, some of them even break the laws of physics, right? So even if we don't break the laws of physics, even then we need very, very stringent latency requirements on radio access of I layer as well. And all of that, in an ideal world, we want to achieve this with nearly same cost and same energy dissipation. Of course, it's not always possible, but we want to be as close to this target as possible. So in terms of timeline, this is another challenge. We want to achieve some 5G related products by 2020, which is now very tight in the sense of standardization as well, because you know standardization has several steps. Again, it's very well known, it's a very complex process and requires agreement between so many entities that usually takes very, very long. So you have to start with a study item, then work item, and then change requests, and then actually some hardware products are manufactured on those standards. So timeline is a challenge. And in order to achieve this huge factor of 1,000, of course, we have to exploit more than one dimension. So some of the dimensions that are very frequently mentioned are increasing the spectrum efficiency using enhanced MIMO, massive MIMO, advanced receiver techniques, coordinated multipoint, and we will see all of them, they affect the backhaul requirements. And then other ones, they are looking at spectrum extension techniques. So in addition to using low frequencies, we want to now exploit some previously unexploited very high frequencies, so millimeter wave and other frequency bands. And again, we want to operate some of the backhaul techniques in those newly exploited spectrum regions as well. So this is also related to backhaul. Finally, the network density has to be increased. In order to increase the capacity, cells will become smaller and smaller. So when we have smaller cells, some of them they will be fed or served using some front haul techniques, and some of them after aggregation will require some new backhaul. This will result in a heterogeneous network, so large macro cells will coexist with these new small picocells, femtocells, indoor deployments of Wi-Fi and so on. And all of this requires some investigation on how backhaul technologies have to actually evolve in order to meet those challenges. Okay, now this is not it. 5G also has several other objectives, just like previous generations of mobile technology they had. It wants to have high capacity, better or full coverage and high mobility scenario catering as well. Should be energy efficient to keep the operator's bills at minimum and to elongate your mobile phone's battery life. Should be able to handle with a huge number of devices, as large as possible. And in 5G, as we said, that machine type of devices will also come into play. That's why you can see that this is specifically a big target as compared to the previous generation. So we need a significant leap on this dimension. We also need reliability. There was a question from the audience this morning. We really appreciate reliable technology. We are all used to technology. We may be downloading our boarding passes on a mobile phone, but still many people, even if they have a boarding pass on their mobile phone, they prefer to print out a printed version as well. That's because of this issue, reliability. Low latency, again, because of tactile internet, here also we need a significant improvement as compared to previous generations. Spectrum and bandwidth flexibility, so we should be able to use higher frequencies on demand. The allocation of a spectrum should be more flexible and cognitive and so on. And higher throughput, which means that even if the capacity is high, if we have a very huge amount of overheads, then the actual throughput is still not significantly higher. So we want to have a system which minimizes overheads and achieves high throughput as well. Now what makes 5G a bit different from previous generations is, again, a very wide range of these diverse objectives we have. So look at the latency. On one side, we are looking at smart meters, which will be served by 5G, which can live with a very large latency of several minutes. Tens of minutes are okay as well. But on the other side, we are talking about tactile internet, which requires latencies of less than 1 millisecond. So a very wide and diverse range of requirements here. Similarly, for throughput, for meter readings, we can possibly be transmitting very small packets occasionally, and the size of the packets is thousands of bits per second. That's a very small data rate. But on the other side, video is a killer application nowadays. For everyone is using mobile phone or wireless technologies in order to download videos, and that will require a very high data rate in several orders of gigabits per second. Similarly, battery life. On one side, we are talking about our mobile phones, and we can afford to charge them after several hours, once a day, and so on. But on the other side, we are talking about those machine meshes in different critical factories and sensor devices and these kind of technologies where it's not feasible to go and change the battery. So battery should last as long as the device itself. So device life and battery life should be nearly matchable. So that's several years of battery life. So because the range is now very diverse, so we have to design a system which actually caters for these wide ranges. And all of these targets, as I will show you in some subsequent slides, that backhaul plays an important role in order to achieve, for example, latency, throughput, as well as energy efficiency of the system. Okay, so one way of increasing the capacity is to deploy small cells, right? And of course, we are not going to scrap all our current macro base stations and then replace them with a high density or ultra dense deployment of cells. Rather, what we do is we have to gradually introduce these small cells without scrapping the previous one. Previous large cells may find a different utility, different use, but for the time being, they have to coexist. So this is the so-called heterogeneous network. So we have a heterogeneity in the system, and that actually corresponds to these three axes that I mentioned before to network density. To increase the density, we have to deploy these small cells which will coexist with the macro cells, and these small cells are of different types. So femtocells, for example, are indoor deployments. We have picocells, which are outdoor small cells. In addition to these smaller cells, we have different other devices or techniques which help in providing better coverage at the cell edge, for example, relay. And then we are also talking about device-to-device direct communication. For example, example was mentioned that if you're making a call from this room across the wall to the other room, your call may be routed. If you are in Edinburgh, your call may be routed back here in London. But if you can have device-to-device type of communication systems, you can avoid that overhead. So all these technologies, they are part of the heterogeneous deployment of the system. And then in the morning, John was talking about the cloud RAN or centralized RAN type of techniques, where you have remote radio heads which are connected through a front hall to a baseband processing unit. So BBU pool, which actually collects all these radio signals and then processes them. So the existence of this heterogeneous network requires a very clever design of these front hall as well as these backhaul links, because actual data traffic after coming through this wireless access has to actually go through these backhaul links to the transport network and core network. Now, something that was presented by John, and he showed us that if you have all the processing on or close or on the tower, and we want to separate or take away some of this processing at the other end in a centralized unit, right? Then we can look at these two as an extreme cases of several other possibilities that we can have. So imagine the current system, everything is done here, and then you are connected to the core network through a backhaul. But now you are leaving the remote radio head here and taking your baseband unit to a centralized location, and this red line becomes a front haul. These are the two extreme scenarios. You can have several intermediate scenarios as well. For example, and these intermediate scenarios are so-called functional split. So you can decide what kind of functionality should be done here at the tower and what kind of functionality you can take to the centralized location. So for example, one case is that you actually transmit your using the standard common public radio interface CPRI type of I and Q signals to your centralized unit. You will need a functional split just after the remote radio head, right? So remote radio head stays here, everything else goes to the centralized unit. You can have a functional split here where actually you're transmitting the subframes over this front hall link. Or you could be transmitting just the received data that is forwarded towards your centralized unit for centralized processing, or soft bit forwarding, or just the MAC type of details in order to coordinate the radio resources between the adjacent cells. So depending on where you have this functional split, the amount of data that will be transported over the front hall will vary as well. So of course, if you have a functional split here, there's a huge amount of data that needs to be transmitted to centralized location. However, if you have your functional split at this location, the amount of data that need to be brought to the centralized location reduces significantly. And this is shown here. So your functional split option A would require around 2.5 gigabits per second. And of course, all of them, they have specific latency requirements as well. And you can see that the most relaxed latency and data forwarding requirements are for the functional splits which are towards your right-hand side, so which is MAC forwarding. So you need a small amount of data to be transported over the front hall, and your latency requirement is much more relaxed as well, because at this stage you are only doing some coordination in terms of radio resources. And of course, you can see that more and more can be done if we are having functional split closer and closer to the radio front end. For example, if we can have a functional split just after the antenna, then we can exploit the intercell interference as a useful signal by doing joint processing. We can have in-network processing. We can have multi-user detection to actually cancel out fully the interference that is caused between the adjacent cells. We can exploit spatial diversity and so on. On the other hand, if we are towards the lower end, the only thing that we can do is, say, for example, avoid interference by scheduling between different radio resources. And we can probably do load balancing between different cells and so on. So again, this slide shows that depending on these different functional splits, A, B, C, D, and E, and different type of exploitation of the available resources, we will have additional requirements on the backhaul. For example, if you are just doing coordinated scheduling, you may have very little amount of additional requirements. But however, if you are doing joint transmission and reception, as here in the last column, you will require additional data to go over the front hall for nearly every of these functional splits. In functional split A, because everything is going on the backhaul, so it does not matter what kind of benefit you are trying to exploit. You don't need anything additional because everything is already going to the centralized location. But from that reference point, if you are doing joint transmission, you need much more data, additional data, to go on the centralized location. Here, the number n actually tells us how many different base stations are involved in this kind of joint processing. So, in other words, how many antennas, radio end, you are bringing to the centralized location. So, n tells us the number of those antennas. So, the message from this slide is that if you want to gain more, joint transmission is the best one. It can exploit actually the interference between the adjacent cells. If you want to have this kind of joint transmission technique, you will require more in terms of backhaul capacity. Okay, so now as we have seen that we require this backhaul to improve, so can we or provide higher capacity, can we get this extra backhaul capacity using the spectrum extension as well? So people have been talking about this millimeter wave and its use in 5G systems. And millimeter wave exploitation in 5G systems looks quite challenging if we talk about using the millimeter wave link between a base station and our mobile device. However, it is more doable if we are talking about a millimeter wave link between two fixed devices which we can align very accurately over, say, for example, mounted on the top of two buildings, and then we can align them, and because they will have pencil beams, so alignment is very important, and then we don't move them, so they are not mobile, they are static. There, millimeter wave can play a very important role, and it can be actually deployed in next few years, and some of the technologies are already there, and some of the deployments are already being used in that frequency band. So looking at this current frequency band, you can see on a linear scale, we are somewhere here on the left-hand side. This is the cellular band we are using. Compared to this, if you see the unexploited higher frequency bands, E band and other millimeter wave bands, they have a huge amount of bandwidth, which is currently not exploited. So we have a lot of potential there, but again, this potential comes along with a very huge challenge as well. You can see that what is the sea-level attenuation, so link loss. Huge link loss for E-band systems, so nearly 100 dB per kilometer as well. And to overcome this loss, of course, either you have to transmit a very huge amount of power, or somehow you should have high transmit antenna and receive antenna gains, or you should be able to form very narrow beams so that the amount of power that you actually transmit is reaching, a vast majority of this is reaching your device, and then you can actually increase the amount of that power at the transmitter end. So the band is has high availability worldwide. It's unlicensed or lightly licensed, and then we can have a small size high gain antennas for this kind of band, and this has restricted coverage obstructed by oxygen and vapor absorption, which is a challenge. So even weather can affect the quality of the link. It has high capacity because the bandwidth is high, and mostly line of sight deployment is considered for these kind of bands, and these are vulnerable to even pole swing. So if you mount the antennas on a pole, even with the wind, if the pole sways, the alignment is so delicate that even with that pole swing, the channel quality will be varying. E-band is a good candidate for backhaul and front haul for the mentioned reasons. Although there are challenges, but at least in this scenario, these challenges might be overcome. Imagine with all these challenges, if we are trying to establish a link between a mobile device and a base station, it's not pole swaying. Even you are swaying, right, and you are moving. So it's much bigger challenge. So human body can also be a shadowing effect, and it could cause a loss of 30 dBs. So that's why, again, using it on mobile phone with a human talking on, so your orientation will actually change the path loss as well. But as I said, if you use it for backhaul technologies, mounting it on the rooftops and aligning them carefully, you might not be getting any human shadowing in between. So that's why these challenges are, you can say, a sort of the order that we can overcome if we are trying to deploy this technology for backhaul usage. Okay. So finally, spectrum aggregation as well. So on different type of spectrum aggregation, intra-band, which means within the given band that is allocated to you, you aggregate several carriers. And interband means, for example, within the current cellular band and then E-band, can we exploit the two bands together in order to increase the amount of data that we want to transmit. And then we are also talking about in 5G having base stations which have two different types of cellular coverages. So for example, one coverage is out of the band and the other one is within the band. So you can have different cell radius for different frequency spectrums as well. So both of these cells are overlaid and can be used depending on the requirements. So each of these cells will require a joint backhaul from the E node B to the core network. So now what kind of backhaul technologies are currently available or are available in near future, and how do they map with the requirements that 5G is posing? So now most of the data that I will now present is collected from the available literature, state-of-the-art literature. So it's more like literature review, putting data together to create one picture. So looking at the downlink and the capacity issues. So on this red line here, we are moving from low capacity backhaul solutions to a large amount of capacity backhaul solution. And this actually shows the range of different numbers that are found in literature. So how much capacity, for example, millimeter wave can provide, ranges from 1 gigabits per second to as high as 10 gigabits per second, and same applies for point-to-point and passive optic networks and so on. So different technologies, you can see how they lie on this axis, which highlights different types of capacity requirements for backhaul. As we have seen before, if we are doing functional split close towards the remote radio head, then we require higher capacity at the backhaul. So possibly the solutions on the right-hand side, they will be more suitable for that kind of functional split. If you are doing it closer to the baseband unit, then a smaller capacity backhaul solutions might also work. And in future, we might have actually hybrid scenarios. So in some remote radio heads, the functional split is happening close to the remote radio heads. In some other base stations, it might be happening away from the remote radio heads and closer to the baseband unit. On the other hand, the other important objective is the latency. And you can see here, this is the most challenging small latency scenarios. And this is a more relaxed latency scenario. For example, satellite has a very high latency. On the other hand, the point-to-point fiber and millimeter wave might be the solutions which have, at least according to the literature, close to the latency requirements that are required for 5G system. So now putting these two data together, what we observe, and these are the sources from which most of this data was collected, because I think the slides will be shared. So if someone is interested, you can go and check more details in these references. So now, as I mentioned this functional split before, here, if the functional split is happening somewhere here, we are doing joint cell processing. If it's happening somewhere close to this site, then we are doing more like coordinated user processing. And this data I very quickly presented that depending on different functional splits, you can see that the requirements of backhaul capacity also varies as well. So highest requirement is for CPRI-based I and Q forwarding, which is the functional split at point A, which is remote radio heads deployed elsewhere, and then backhaul bringing them into a centralized or cloud radio access network. And this is what I was mentioning, that depending on what kind of option you are trying to opt. So for example, joint transmission is one of the most advanced signal processing option. So this requires a lot of additional backhaul requirements for different types of functional splits. So for example, this was functional split A, B, C, D, E, and so on the previous slide. So for functional split B, you require additional 200 megabits per second for coordination and for overhead messages and so on. And joint reception and multi-user detection and all of these techniques, they have different additional requirements. So to get more out of this arrangement of distributed antenna system, to get more out of it, you need to provide a more stronger or higher capacity backhaul. And then another important point that was missed in some previous tables, I just highlight this column here, which is for different technologies, right? This distance is important as well. So they provide a specific level of latency, they provide a specific throughput, and meet some error targets, but they have a range or length as well for which they meet these specifications. So this distance is another important aspect. So for example, if you have a very dense deployment, but you have very few baseband unit or Cloud RAN locations, then you will need longer backhauls, and then you need a technology which actually provides that length of the backhaul. So this is just for reference in the slides, different type of technologies, how much range they can provide. So this brings us to this diagram here, which says, okay, going from this kind of one extreme of the functional split, which is remote radio head deployment and Cloud RAN, and then the other extreme of the functional split, where we are doing more or less just coordinated scheduling between adjacent base stations, we can see what kind of technologies can meet the requirements of downlink capacity. So for example, for this extreme case, the technologies which meet this requirement are millimeter wave, free space optic, and then next generation passive optic networks and point-to-point fiber, which are all very expensive, difficult to deploy, have a lot of technical challenges with them. So as you keep on moving with more relaxed coordination techniques, of course they relax the backhaul requirements, and then you have more options available to you. So even here the millimeter wave at 60 megahertz will become usable, GFast becomes usable here as well, and then Ethernet PON and gigabit PON, they are also feasible technologies. So as you keep on moving towards the right hand side, more and more technologies, they start meeting the criteria, and they are usable for possible backhaul solution for that system. So what happens to latency then? For latency, in order to do these kind of operations, the techniques, the backhaul technologies which meet the latency requirements for functional split A, B, C, and D are point-to-point fiber and millimeter wave. And of course, in addition to these two, the passive optic network and sub-6 gigahertz backhaul, for example, microwave backhaul, they also become feasible for E and F as well. So there is a typo, so that should be F as well. So now here JT and JR means joint transmission and joint reception, and this coordinated scheduling and coordinated beamforming, CS and CB. So joint transmission and joint reception is more demanding in terms of the data requirements, so that's why it's on the left-hand side, whereas coordinated scheduling, coordinated beamforming is the least demanding coordination technique between the base stations. So now we come to some backhaul research directions. We saw all different technologies and how they really meet the requirements for different types of backhaul arrangements or different types of functional splits in the implementation of the centralized or Cloud RAN. We look at some research directions. So research on backhaul, 5G backhaul is prolific and overlapping in the sense that it has several promising directions, and some of them I have tried to identify here. Like one is wireless backhaul. So should it be, if it is wireless, should it be in-band, out-band, should it be using millimeter wave, or just stay in the other conventional bands and so on? Should we be using software-defined network, virtualization of transport network, as mentioned in the morning as well? So we have all these hardware resources. So software, which is sitting on top of this hardware, can we somehow virtualize the availability of this hardware? Then, of course, there will be several benefits of it. It will be, if it is virtualized, many operators can share that hardware and so on and so forth. Now, energy efficient provisioning. Now, this has become even more important. Previously, the focus of energy efficiency research was either on the mobile device or on the radio access side, because they were the most energy wasting parts in a wireless communication link. But now the focus is shifting to backhaul as well, because in heterogeneous network backhaul, an amount of energy consumption or the contribution of energy consumption is 50% on the backhaul and 50% on the radio access. While previously it was only 5%. So when it was 5%, it was not that important. But now, when it is around 50% for small cells, then backhaul energy efficiency becomes very important as well. Caching at access nodes and devices in order to relieve the backhaul. So we do not want to transmit everything always through the backhaul. If possible, we should be able to cache it on the edge so that it can be directly downloaded or served from the radio access unit without fetching it through the backhaul. joint design of radio access network and backhaul. Again, this is an optimization problem. Adaptability and flexibility is enabled through self-organizing networks. So because now the backhaul has several options available, and all these options are not always optimal for all scenarios, and scenarios keep changing. So if somehow you can change the configuration of the backhaul as well as the scenario or traffic or requirements change, then you can keep the network optimized at all times, for example, during the day, during the night, and so on. So looking at the millimeter wave backhaul, should we be doing it like in band or out of the band? So for example, these are the macro cells, and then there are some small cells available as well. And then this is a ring topology backhaul connectivity, and then one of the base station is then connected through the core network. So this kind of backhaul is also established through wireless links. So that's why you see these antennas here which try to establish those backhaul connections. But now the question is, should we be doing it in band or out of band? So in this example, if we are doing it out of band, then of course the E band or millimeter wave band becomes an extra resource that is dedicated for backhauling purposes, and that does not affect the local operation of these macro cells. There is not enough interference in them. However, we could also do it in band as well, and this is one of the work where the authors are trying to see what is the cost, how cost effective is the in-band usage. So the same frequency band is shared for radio access as well as for backhauling. So depending on the load on the backhaul and load on the radio access, you can share the amount of a spectrum between the two techniques, and what you can see is that the instantaneous capacity of the backhaul and the radio access, both for uplink and downlink, can be optimized using different algorithms or techniques as presented in a paper down there. So now another research direction is what kind of technique would be more feasible in terms of playing with backhaul and front haul. If, for example, you have this radio unit, and this radio unit has to provide service on this side as well as connect to the Cloud RAN as well. So if you're using an in-band frequency resource, should it be doing it over time division duplexing? So how those timing slots should be optimized in order to get the most out of this backhaul connectivity. So a fixed partitioning solution, or rate balancing partitioning solution, or without rate balancing an optimal partitioning solution, you can see the performance of all these systems. They differ significantly in terms of their spectral efficiency service to the user. Of course, details of how this is optimized is in that paper. I'm just highlighting one area of research. And then here we look at the software-defined networking applications. So you have a lot of hardware here, and you have different techniques or algorithms like topology discovery, service recovery, caching, load balancing, and so on. So this is more like a software. So SDN controller is trying to virtualize this hardware for the use by these algorithms on top here. So if we can do that, then we can have a lot of better optimization techniques in order to exploit the resources in more efficient manner. Now green, backhaul energy consumption. So as you can see, that the impact of backhaul in actual macro cell network is just 5%. So if you try to see the energy consumption with and without backhaul, the difference is only 5%. So 5% is being consumed by the backhaul, so that's why it was not that significant. However, if you look at the heterogeneous or small cell ultra-dense deployment network, you can see that this difference with or without backhaul is significant, nearly 50%. So half is being consumed by just the backhaul, and the rest is being consumed by the radio access network. So here, in this case, it's needless to say that optimizing the energy efficiency of the backhaul also becomes very significant and important. Everyone knows that energy efficiency is very important for the operators as well, because they pay a huge bill in terms of keeping their networks energized. Yes. So evolution of backhaul technologies for energy efficiency again. So backhaul energy consumption can be optimized by, for example, switching off the unnecessary backhaul links when they are not needed. Just like we can optimize the energy consumption of radio access units when we can switch off the either remote radio heads or base stations or small cells when they are not needed for extra capacity. So doing this jointly with an objective not to increase the delay in actual service, right? Keeping the offered traffic as high as possible and keeping the delay as low as possible. We want this energy saving to be as high as possible. So of course it becomes again an optimization problem that can be solved using some clever algorithms as given in some of these papers identified here. And this is part of the work of one of the EU project, Bungie. So caching again. So as I mentioned before, backhaul becomes overloaded whenever data is fetched from the actual core network or from the internet, right? Then it has to come through the backhaul, through the front haul, and then to the actual access point which actually delivers the data. And of course the reverse happens when the uplink traffic is going towards the core network. Now if you can identify the popularity of a content, then you don't have to fetch it always from the actual source. You can either cache it at the gateways or cache it at the actual base station or cache it very close to the remote radio head if possible. So this caching, content, highlighting the or identifying the content popularity, and then based on that popularity you can optimize the location of the content in terms of both space and in terms of time as well. This will of course increase the available data rates if backhaul load is relieved, and then this requires use of distributed algorithms in order to realize a self-organizing networking functionality, because somehow network has to learn about this popularity automatically. You don't have to have engineers which optimize the data, analyze the data, and then identify their popularities as well. So what has been identified in some of these papers is that cache-aware user association in backhaul-constrained small cell networks can optimize the operation of the network. And you can see here that number of small cell base stations, as you increase them, then average utility per UE also increases in terms of bits per second per hertz, or throughput of that also increases. However, this increase can become limited by the backhaul, because backhaul has a finite capacity. However, if you start to do caching, then you can overcome this limitation, and then as you increase the number of base stations available, then the average utility per UE also increases. Now, I think it's one of the final research direction slides. So we are looking at joint radio access network as well as backhaul design. So if we do this optimization separately, for example, if we optimize the backhaul for a static scenario and we optimize the radio access separately for a static scenario, then this overall or globally it might not be an optimum solution. So somehow, depending on the requirement from the core network or from the actual internet where the data is coming from to the actual UE, considering it as a single link and then jointly optimizing the backhaul available solutions as well as the front haul available solutions, that will give the best utilization of the available system resources. So that's why we can say that our system should be both backhaul and radio access network aware at any given instant in time. So this also requires a functional design which is considering both RAN and backhaul simultaneously. So if you have a backhaul which is energy aware and also performs intercell interference cancellation, then of course you can optimize the performance of the system. Here what you observe is there is a trade-off between energy efficiency and spectral efficiency. So you have a sweet point or optimal point where energy efficiency is optimized as well as the spectral efficiency is highest as well. And this sweet point or optimum point is different for energy efficient allocation or just greedy rate adaptive allocation in the system. So we have to optimize the backhaul links as well as radio access technologies in order to operate at a point where the spectral efficiency and energy efficiency are simultaneously maximized. Now finally, you have this different learning techniques, or for example, fuzzy Q-learning based. So Q-learning is one of the reinforcement learning techniques for radio access network as well as backhaul. And we also talked about this discontinuous transmission in the morning, which is the correct way of doing things. You do not make the network available all the time, rather you make it available when it is needed. So it's always there, but not always switched on. So it only gets switched on when it is actually required or needed. And here what you observe is UEs per macrocell sector, so which is the load on the macrocell. So as the load increases, the small cell network's energy efficiency keeps on decreasing. So the reason is because you cannot switch off many of them. So if the load is low, you can switch off some of the small cell network nodes, and then you can save in terms of energy. So what's the vision? What are the requirements that we are looking for the 5G backhaul? We need a flexible and adaptive, software-defined network-based and self-organizing network capable design, which is doing the designing jointly between the radio and backhaul, radio access network and backhaul. Why we need all of these adjectives in order to have a functioning backhaul for 5G? Because in 5G we may have to actually enable multi-operator cooperation, multi-vendor operation of the system, multi-technology. Multi-vendor, multi-technology is already in previous generations as well, but multi-operator, where operators are sharing different hardware resources, is already starting to happen, but requires a further help from the technology in order to realize it. And then we also want to realize resource pooling. So John also mentioned in the morning that one of the advantage of having this Cloud RAN architecture is that you have a lot of resources which are now pooled together. So you can better optimize or increase the exploitation of these resources rather than having them at different places. Even if they are not needed, they are there, but you cannot exploit them. So bringing them together will increase the possibility of exploiting them at 100% level, so that increases the efficiency in terms of reduced capex as well as opex of the system. Now, energy efficiency, infrastructure efficiency, spectrum efficiency, utilization efficiency, all of that will increase if we have a centralized software-defined network-based scenario for the backhaul. Flexibility and scalability is required because you saw that how many devices per access point are needed, and the system is scaling exponentially. So of course we need a solution which can cater for that. Flexibility because traffic is not constant throughout the time, and if you just make the backhaul and radio access static, then you cannot adopt the network according to the changing dimensions or changing requirements of the network. And that comes to this last point of adaptability as well. So it should be able to respond to changes in the scenarios changing in the environment. So this brings us to this concept of backhaul as a service. So which is a concept in software-defined networking. You have all these technologies. You have passive optic network, millimeter wave, microwave, DSL, free space optics, sub-6 gigahertz. All of these heterogeneous backhaul physical technologies are there. And then you have several backhaul objectives to meet. So backhaul as a service should provide caching, mobility, energy efficiency, load balancing, and so on. Similarly, RAN is also offered as a service. So you can have one radio access, two radio access, depending on your requirements, right? So everything is in a shared pool, and depending on your requirement, you ask for different radio access network services, and you ask for different backhaul services, and then you optimize your whole link from the core network to the user equipment. And this requires some common intelligence between the two, which can be actually done in a self-organized manner. So this brings me to some of the recent results that we have. I will take just 10 minutes to present those results just in the interest of time, and then we will open up the session for questions and answers. So these results were also presented at recent ICC, so some of you might have already attended that session. So this is some joint work with my PhD student Mona and my colleague Rahim Tafazuli, and then Anwar Tukmanov is from BT. So this work is jointly sponsored by BT and EPSRC. So what we try to see here is, if we have a joint deployment of a macro cell and a small cell, then usually the path loss of the small cell becomes equal to path loss of the macro cell if you do the link budget at a specific point here. But the signal strength of a small cell becomes equal to the signal strength of a macro at a different point, because the small cell is, first of all, sending a smaller amount of power from its transmitter. So that's why that happens at a different point. So ideally, a small cell can expand its range up till this point by increasing the amount of transmit power that it has, or by using an artificial factor in order to just extend the cell range. What will happen if the cell range is extended? So any users in this region will be associated with the macro cell unless you expand the boundary definition of this small cell. So as the small cell expands its boundary definition, it will encompass more and more users to be served by the small cell. Now, by doing that, we will be offloading the macro. However, what will happen is, by transferring the load onto the small cell, we are increasing the load on the backhaul that connects this small cell to the core network, right? So this is more or less a trade-off problem. So how much we want to offload to the small cell, depending on how much backhaul or front haul is available to that small cell or radio access unit back to the core network. So this is achieved, this variation in the cell range is achieved by introducing a cell range expansion offset factor. So if these are in dBs, then you add this factor into this small cell signal strength, and that gives you the threshold where this boundary would be. So when a small cell signal strength of the small cell plus this offset factor is equal to the signal strength of the macro, then we will define this boundary at that point. So I skipped these details, and I think I can move on to these were some results from some previous papers which have tried to solve this problem, and I move on to the actual results we have. So we deploy a scenario of 3-sector scenario, and within that sector we have some small cells as well, and there are 3 types of small cells. One which is relatively close to the macro base station, the other one which is at a medium range distance, somewhere in between close and cell edge, and then there are some small cells which are deployed at the cell edge. So of course, for the simulation purposes, there were several runs that were made, and several different type of snapshots were produced in order to get the average results, but I have just taken one snapshot to explain what's happening in this kind of system and how backhaul and radio access are being optimized. So I skipped the details of, they will be in the presentation shared on the workshop slide. I just show you some of the snapshots from the simulations, and then some results how Q-learning can help in optimizing the traffic and offloading the backhauls when done joint optimization. So here what you observe is, look at that diagram here. So these red cells are being served by the actual millimeter wave backhaul. So there are 2 types of backhaul that should be mentioned. So these small cells are either connected by a millimeter wave backhaul or a VDSL based backhaul. So millimeter wave backhaul has some outage event. So sometimes it, with certain probability, say 16% or 10%, it can be an outage. VDSL is reliable, but it has smaller capacity. So millimeter wave high capacity, less reliability. VDSL has high reliability, but smaller capacity. So with certain snapshot, some of the cells, they are connected with millimeter wave, some of the cells, they are connected with actual VDSL connection. Okay, the second point is the cell range expansion of offset. So either it's 0 dB, which is the conventional system, so no offset, 6 dBs and 12 dB. So higher is the offset, what you can observe if you just focus on this block here. So if we increase this offset, more and more cells becomes green. What green means is that UEs are served by small cell with the shared bandwidth. So here, when there is no offset, even these cells, they are very close to this small cell, but they are still being served by the macro. But as you increase the cell range expansion offset, then more and more cells which are close to this small cell, they come into the coverage range of that small cell. Keep in mind there is shadowing effect as well, so that's why it's not always geographic based, so it's based on the signal strength. So there are two scenarios. Either we have a dynamic cell range expansion offset, so either we fix it to 0, 6, or 12 dBs, or we can have a static, sorry, if we fix it, or we can have a dynamic cell range expansion offset. What is dynamic one? Dynamic one is the one which actually adopts the cell range expansion offset depending on the available backhaul. So if it is millimeter wave backhaul and it is available, then you have a lot of backhaul capacity. You can increase your cell range expansion offset to bring more and more users within your service area, and because you can serve all of them. If you have a VDSL link, your capacity reduces. So that's why you reduce your cell range expansion offset in order to offload some of the users back to the macro cell. So how do we do this? Of course, this has to be done in a self-organized manner. So that's why we introduced this Q-learning based technique. So if you run the network, over the time the network learns how much capacity requirements or backhaul availability, backhaul reliability we have at this given small cell, and then based on that it adopts its cell range expansion offset. So here we now observe some of the effects. So first of all, if you look at these different colors, so cells with millimeter wave, they are colored. So these cells, they are being served by the millimeter wave, and these gray ones are being served by the VDSL link. And now within those millimeter wave ones, you can see the ones who are close to the base station, they are blue in color. Medium range one is green, and the one which is at the cell edge is the red one. And this is identified here on these lines as well. Now the crosses on these lines, they show the events in the simulation where millimeter wave was in outage. And what you can observe here is that the outage events, they are aligned by the peaks in the backhaul or by the troughs in the backhaul event. So you can see that the throughput is affected by the outage of backhaul of red cells. So why is that? Because when the red cell backhaul is an outage, right, then these red cells, the users here in this red cells may not be served directly by the macro cell. So that's why the throughput decreases significantly. So these small cell antennas, they are very, very critical, especially for the cell edge users, because it's very difficult to serve them directly with the macro. However, when there is an outage in blue or green, then users are actually offloaded to the macro, and still we have significant throughput. So main dips in the throughput event, they are aligning with the event when the cell edge, a small cell backhaul goes in outage. So you can see there is a dip here as well, and then there is another big dip here, as identified by those blobs. Now users in the midway hotspots, or the ones which are close, so those green and blue cells, they have the option of camping on the macro. So whenever the backhaul goes in outage, so these other crosses, they camp on the macro. Whenever their backhaul is in outage, number of users on macro cell peaks. So that's what is shown. Look at any other crosses here. So that will always increase the number of users on the macro cell. So these are the camping events. So whenever the backhaul goes in outage for a cell closer to the base station or in the mid range, then you always have a peak in the number of users on the macro. Now, what is the final benefit of this one? So users in cells without the congested backhaul, smaller is this number, the better we are, because this means that these users still get the service because their backhaul is not congested. And you can see that using this Q-learning technique, this dashed black line, the number of users which have this congested backhaul significantly decreases. More or less, it stays to a smaller number as compared to the red scenario where it's always a high number. So what we are doing is using this dynamic cell range expansion we redistribute the user association while maximizing the throughput and minimizing the users who are served by cells with blocked backhaul. So it brings in intelligence into the network. Whenever the network or small cell sees that the backhaul is now congested, it either compresses its cell range in order to offload them to the macro. Okay, so if you look at the small cell location, if it is close, the probability of congestion on the front haul over the 900 iterations of the simulation is more or less 0%, but average is around 1%. When it is very far, this is significant, around 20%. So for different scenarios, the scenarios that we considered, we had 1/3 millimeter wave, 2/3 VDSL backhauls, and then all millimeter wave or all VDSL backhaul, or final one is a configuration where we have always the millimeter wave, but as a backup we have VDSL. So we increase the reliability by having a backup, right? And that is the best performing scenario. So you always have the high capacity option, but if that option goes away, you still have a fallback low capacity VDSL solution to serve the network. So no cell goes in outage in any given scenarios. So I think I have mentioned these insights. So I just conclude with some very quick outline of the future work. So we know that CRAN has RAN advantages over distributed RAN or the current distributed RAN scenario. It enables advanced features. It is cost effective in terms of RAN, as mentioned in the morning in detail by John. So it reduces both OPEX and CAPEX. And then, however, this distributed RAN has a backhaul advantage. Why? Because in this scenario, most of the processing is done close to the remote radio head, and very few amount of data has to be brought to a centralized location. So for a cloud RAN, maybe fiber, point-to-point fiber, or some technology which has very low latency and very high capacity might be a must prerequisite, right? And the research question is, can millimeter wave fill in the gap as well? If you look at backhaul and RAN, where is the optimum functional split? So as I discussed throughout the presentation, the different functional splits and different amount of processing that we want to do requires different solutions. I can skip this one. Now, adaptive and flexible routing is an important one. So in given scenarios, you may have different type of links. You may have multi-hop link. You may have a direct link to the baseband unit. We may have a hop through a wireless link as well. So depending on different type of application, for example, if you have an e-health critical, latency critical application, you adopt a different route. If you have a machine-to-machine type of application which has more relaxed latency requirements, you may adopt a different backhaul route in order to load distribute all the available diverse or heterogeneous backhaul solutions you have, right? So, and this works both for uplink and downlink, right? And then in order to operate backhaul as a service, you need to split the architecture in terms of both data and control functionality. So these macro base stations may be responsible for providing the control functionality in a large umbrella service area for all the small cells. However, the actual data functionality is taken care of by the small cells themselves, and they actually linked directly through an uplink front haul or backhaul to the centralized baseband unit. So this is so-called future architecture with split control and data plane. Right. With this, I conclude my presentation. Thank you very much for your attention, and if there are any questions, I'm very happy to answer. Thank you.